So, division concepts. I first want to have a little conversation about connecting the operations. And it's really vital that we start to think about our operations as being intimately related. Because what we have here is we have inverse operations. So if you add something, you can invert it or undo it by subtracting. And then we have this notion of repeated addition that gets us from addition to multiplication, and repeated subtraction is what we'll think of division as. And then these two are likewise inverse, or they undo each other, right? Because if we think of it up top, if we have a single addition, a single subtraction will undo it. If we have repeated additions, repeated subtractions will undo it, right? And so thinking about, and that's why we talk about them in these order, and you'll find that textbooks tend to treat these back and forth because there's even a standard that says that students should be able to work between operations and their inverse. So it's an important skill that children develop to be able to work fluently between these different operations. Now, so I've kind of hinted at one of them is we can start to think of division as repeated subtraction, the inverse of multiplication. But I'm going to start with, just like I did with multiplication in the standard, this is the 3rd grade standard. And again, that top red banner there, the CCSS math content, 3 order and operations, that gives us a link directly to these words. And so students should be able to interpret whole number quotients of whole numbers. So remember, we're still working in whole numbers. We aren't working with any fractions yet. So when we divide, we're either going to be able to divide evenly or we'll have a remainder. A decimal, because that's just another form of a fraction, isn't defined and it doesn't mean anything in this context. So children should be able to interpret 56 divided by 8 as either the number of objects that each of 8 people get when you share equally, or as some number of objects, or how many people could we share it between if we have 8. So I'll say that again. The first meaning is 56 divided by 8. I'm going to split 56 among 8 people. How much do they each get? And the other is, I have 56 objects. I'm going to give 8 to each person. How many people can I give objects to? And that's precisely these two meanings. And so here it says, for example, children should be able to describe a context in which a number of shares or a number of groups can be expressed as 56 divided by 8. So our friend from last time, we have our m times n equals p, our meaning for multiplication. And we kind of have 2 ways we can think about this. We had how many groups division, some number of groups times the size of each group will give us a product, which is what we write as p divided by n equals who knows. And so for an example of that one, you ate 8 cups of popcorn. 1 serving of popcorn is 2 cups. How many servings did you eat? So we know that each group here, in this case serving, has 2 cups of popcorn. There were 8 total. So we divide it and we say you ate 4 servings of popcorn. Now in the other case, how many in one group? So we have m times something is equal to p. And that we would write still p divided by m now instead of n. And an example here, you ate 8 cups of popcorn. 8 cups of popcorn is 4 servings. How many cups of popcorn is a serving? And so you know that in total there are 8 cups, and you can split that evenly amongst 4 people, so how much ends up in each of those? No. Yes. That's precisely right. It's even there. So this is an example, right? So this is another idea of this mathematics knowledge for teaching or pedagogical content knowledge, this really kind of specialized knowledge that we develop as teachers. And so there will be times where I'm going to say something and I'll pause because I'll be like, wait, is that really how many in one group? and in this case, I'm convinced it is. And so putting those, just to summarize, putting them next to each other, if m times n equals p, and I'll write that here at the top, if m times n is equal to p, we have two interpretations for division, that is p divided by n, which was this, how many servings, or how many groups, or here, how many is a serving. So we're looking for the size of one group. And so those are really the two big meanings of division, and we're going to work with those today. If you are in class on Wednesday of this week, we're going to be doing an activity where we work with these two meanings of division, and we practice looking at a word problem. We decide, is this how many groups or how many in one group? And then eventually you'll have to write some of these problems. And in terms of developmentally, which one's easier? How many groups? Wait, how many groups? That one over there is the easier, because how many in one group is kind of what we call pre-algebraic thinking, because you have a placeholder. There's 4 servings, but we don't know the size. So 4 times what's equals 8. And you'll see in a couple slides that this 4 times what's, rewriting it as a multiplication problem, is actually one of our strategies for handling division. So some models. So we have 3. So you'll notice that we come out with fewer and fewer. And I don't know if it's because nobody's come up with any great models, or the ones we have are good enough. And I actually think it's the latter. The ones we have are good enough. And the reason for that is we have this missing factor model. And so that essentially, and I will talk about this a bit, hinges on just taking a division, making it multiplication. And then we had a bunch of representations for multiplication. And so thinking about, all right, if we know division and its inverse is multiplication, we have all these models here, we can just move to multiplication, solve it, and then translate back to division. So our set model. So the set model is the set of elements representing the dividend, so the answer you get at the end, is partitioned into, no, that's not at all it. What we have here, the dividend, our number, divided by the divisor number of subsets. Example. Suppose we have 18 cookies and want to give an equal number of cookies to each of 3 friends, so this fair share. And you'll notice that this fair share is a super common context that we use, and the reason for that is because it tends to be relatively relatable. So we have 18 cookies, and we want to give an even number to Bob, Dean, and Charlie. How many should each person receive? Well, if we draw a little picture, we have our 18 cookies, and we're going to share them evenly amongst Bob, Dean, and Charlie, and that is what we end up with. And so since each of those 3 ended up with 6 cookies, we say that 18 divided by 3 is 6. Set model, fair share. And our words for those are dividend, divisor, and quotient. So the dividend is the number that's being divided by the divisor, and the thing you get at the end is called the quotient. The quantity at the end is a quotient. And so another way we could have solved that problem is, so if each friend, they're going to get some number of cookies, say it's C, right? Then the 3 numbers together, or the 3 friends together, get 3 C cookies, so C plus C plus C, which is still in total 18 cookies. So 3C has to equal 18, and since we know 3 times 6 is 18, that 6 we have there is our missing factor. And so we get the answer as 6 through multiplication. And then our last model is repeated subtraction. So suppose we have 18 cookies and we want to package them in a cookie box that holds 6 cookies each. How many boxes do we need? Well, first, we take 6 out to fill a box. 18 minus 6 is 12. And then we take 6 more, and that fills our second box, and we have 6 cookies left. And so now we take the last of the 6 cookies to fill the final box, and since we needed 1, 2, 3 of these boxes, we can say that 18 divided by 6 is 3. 18 divided by 6 is 3. I don't know why that's animated. I don't remember adding an animation. Okay, and so multiplication, groups of a certain size give us a product. Division, some number of objects, either being fairly shared between a given number of people or a certain number being given to each person, how many people are there, right? And so those are those two, how many groups, how many in one group. And so we have ways that we can do this, moving beyond these really representational models where we have dots or where we have cookies or we have something like that. So for example, what they have here is 32 divided into 4,224. And so this is called partial quotients, and all of the work is there, but I'm going to work through it because I think it's one of those things that's really actually helpful to see. So we'll just write our original 32. I drew that more like a square root. 4, 2, 2, 4. So I'm going to put some scratch work over here. I know that 32 times 10 is 320. I know that 32 times 100 is 3,200. That'll work for now. All right. So I know I can take at least 132s out because 3,200 is less than this. So I'm going to start with taking out 100. 100 times 32 is 3,200. We can subtract 4, 2, 0, 1. 1024. Well, there's 320 is smaller. 640 is smaller. 640, 980 is also smaller. So I'm going to take out 30 of these. So 30 times 32 should be 960. Hopefully that's what I just said. Subtract it. 4 minus 0 is 4. 2 minus 6 we can't do, but 102 minus 96. So this is one of our lovely subtraction strategies. 102 minus 96, I don't have to do any rebundling. It's just 64. I know that 132 is 32, and 2 of them is 64. So I have 2 more, 64, subtract them, we get 0. So we get 100 plus 30 plus 2 is 132. So we have, and so that's the work over here. And notice they wrote it out. They took 100 of them out. They took 10, or they're like, oh, I can take 10 more. I can take 10 more. And then they took out 1 and 1. And we're left with 132 times 32 equals 4224. So that, I think, is I see. And we use partial quotients because it's a standard algorithm as we get there. At every step, our goal is to get the absolute maximum number of divisors. And if we can't, we try to find some, and right, and so our goal is to find the most we can take out at each next step. But here, you don't have to. You can just keep taking 10 out as long as you then add them back in, right? You can take 10 out 3 times like they did above me, and just making sure that each of those gets taken into account. And it also means I didn't have to find 30 times 32. I could have just subtracted 320 twice, right? Because it's repeated subtraction. That is important enough to write. Here's literally the repeated. I'm using the wrong end of my stylus. Repeated subtraction. You can't read that. I apologize. It says repeated subtraction along the right-hand side. And now the standard division algorithm. How do we begin to motivate how this works? So if we look at the question, represent 726, or the question is, what is 726 divided by 6? So it says represent 726 with base 10 blocks. And so this is something that you're going to do when you're first introducing multi-digit division. This isn't how you're going to work out a problem, but rather going to be how you really reinforce the connection between the algorithm and place value. Because remember, when we work with the standard multiplication algorithm, we ignore place value for the most part. We're really just working with the face value of the numbers. We're following a process to put them in the right place, and then when we add them up by place value, it works out. And so this is really this step of enforcing or reinforcing place value before we move to the standard algorithm. So we want to divide it into 6 parts. So suppose you're dividing into 6 groups. How much is the fair share of each group? Well, you can start by seeing how many groups of 6 you can take out of the hundreds. You can take one set of 6 flats out of our number 726. Is that my original number? 726. We can take 1 6 out, one set of 6, so this is 600. That we can take out, and then we're left with 126. 100 plus 20 plus 6. And now we look at the tens, so we have 12 of them, and it's how many 6s can we find? Well, it turns out we can select by splitting that 100 into longs. How many groups of 6 can we take out of that? Well, we can take 2. Right, we can take this top set of 6 or the bottom set of 6 longs. And so far, we've taken out 600. Each of these is 60. So we've taken out 720 so far. And we still have some left over, so we're not done. There's one group of 6 here, which has 6. So there's 600, 60, and 60. And so if you add those back up, we still have 600, 120, 6, 7, 26. Still the number we started with, which is important. But then what we actually end up having then for our result, because that's our product, why I cannot draw a divides to save my life, it seems. Because what we're looking for is 6 divided in to 726. So when I fair share these, I'm going to pick a different color. Each pair, or each group will get one of my hundreds. They'll get a 10 from here. They'll get a 10 from here. And they'll get 1 from here, which means they have a flat plus 2 longs plus a unit, which is 120. And so that's how we see the 121 using place value. Because what we do is first we take our hundreds. How many can we share that between 6 people equally? Yes, we have 100 left over. Regroup it into tens. How many groups of 6 tens can we get out? Is there any left? In this case, no. Look at the units. How many groups of 6 can we get out? Just 1. And then we're done. And we can see that parallel process here in the repeated subtraction strategy. So what we end up having here is we have those 100 6s, or as I was saying, 6 100s. And then we had 126 left, and we could grab 2 of those groups of 60. So we have 6 tens. And here we have 6 tens. So we would have 600s. 6 tens, 6 tens, and then we were able to take 6 ones. So that's one of these, two of these, one of these, 121. Or, more compactly on the right, 726 divided by 6. We take 100 of them out, and we get the 600. We subtract that, and so I'm going to be a particular stickler about this. Would really appreciate us writing our subtract signs to remind us of what we're doing at each step. It's good practice in general to follow your work, but also extra good practice for working with children. But, right, whether or not you did each of these 10 separately or some other combination, you will get the same answer, assuming you didn't make a mistake. And so this is another one of those reasons why Polya's looking back process is really important. Because we have multiple algorithms. It's not that one's better than another or worse than another, but specifically, it's important that we have access to all of them so that they can choose the strategy, they being our students. Our students can choose the single strategy that works best for them. And so here you have multiple strategies. You can complete it one way and then maybe check it with a standard algorithm, right? Because I'm going to assume that most of us are familiar in some way with the standard algorithm. And so what I want us to do is think about, okay, that's the standard algorithm. That's our go-to check in the background. And so what we have there is our go-to checking situation. We can go back, we can look at our standard algorithm and check our work. But we should, when we're learning these new strategies, like repeated subtraction, is do it the new way, the repeated subtraction way, and then double check with the standard algorithm. Or do it the standard or the repeated subtraction way and check it on our calculator, right? And so we want to go back because showing our answer more than one way increases the confidence we have when it comes to talking about our answer, right? If I can show you I got that answer 2 ways, it's going to be more convincing. And then here are just a couple other representations of how exactly this could work. So here on the left-hand side, we still have that 121, and then what I'm going to show you, that's really the same exact process that I followed when I wrote the 100, the 20, and the 1. And then here on the right is our standard algorithm. And so let's see, I'm always rusty when it comes to using the standard division algorithm, but I think it'll be worthwhile for us to practice this together. So let me bring up our writing. And what we end up having is we have 6 divided into 726. And so we go, 6 goes into 7 one time, we put a 6 and we subtract 1. And bring down the 2. 6 goes into 12 twice, that's 12. Subtract, we have 0. Bring down our 6. 6 up here goes into 6 one time. 6, subtract 0, and we're done because there's none left over. But all of this corresponds to place value. It's just we don't talk about it. Or we don't think of it in that way anymore. Because just like standard algorithm for multiplication, our goal was efficiency. When we use the division algorithm, our goal is efficiency. Children need to have an understanding of the concept of division, the meaning of division, what precisely it is that we're doing. We're seeing how many 6s are there inside that. If I took 726 of some object, let's think something small that would make sense. Maybe like grains of rice. I don't even have a concept of how many grains of rice is. I got nothing. You have 726 of something. Widgets, so that's a go-to generic term. You're going to share it with 6 people. How many do each person get? Right? Each person will get 121. But really, what we're doing, and I'll write it in blue, 6, 7, 26, we're saying, and that's the reason, so notice in multiplication, I'll write this in the corner, because this is a worthwhile aside. If I have 24 times 6, I start on the right and I work left. I do my 1s times 1s is 24. Carry the 2. My 1s times my 10s, 12 plus 2, 144. But when we divide, we work left to right. And again, remember, it's a question of efficiency. So it's, if I need to put these in groups of 6s, looking only at that 700, how many 6s can I guarantee are in there if I take them out? 100 at a time. And the answer is, or if I take out, how many, see, this is where it's like, okay, make sure the words that we say are precise, because what we're talking about is not the way that we often think about division when we're calculating it. We can take 100 6s out of 726. And that 6 goes here because it's really 600. We subtract. We have 100. And then we really have 126. And then we're like, okay, so we did all of our 100 6s we could. How about our 10 6s? Well, if I only look at those digits, I can fit 2 60s in there. So this is 20 6s. Subtract, I added my place value 0. I wasn't supposed to, because I wanted to write it in orange. I'm going to write back over it. We'll just go with it. And then here we have 6. But now we have 1s, and we can get 1 6 of 1s out of there. So let's see if I can now step back through this. What we did over here, we said there is 1 6 and 7, so we can subtract, and we're left with 1. And we said there are 2 6s and 12, subtract it, we had none, had to bring a 6 down, there's 1 6 and 6, and we're good to go. But in terms of place value, what's happening? 726. I can take 100 6s out. That's 600. 726 minus 100 6s is 126. Then 10 6s is 60. I can take 20 more of those out. That's 120. 126 minus 120 is 6. And then if I have a 6, how many 6s can I take out? The answer is just 1. So 121. And so, yeah, I think of the operations, division tends to be folks' least comfortable. I think that's true particularly of elementary age kids, but I think it's true of adults as well. I think about division tends to be this one that we struggle with a little bit more. We often will see that we'll have a child that is really skilled at dividing with the standard algorithm, just be able to do it, but then trying to push them to think, why is it that you're doing those things? Why do we care that there's 1 6 in that 7? And it's because we have 726 as our original number. And we want to say, all right, if we take our 6s out 100 at a time, how many times can we do that? Or if we take our 6s out 10 at a time, how many times can we do that? Or if we take our 6s out 1 at a time. And actually, that's the phrasing I think would be really great to use. If we take our 6s out 100 at a time, we can take one of those hundreds, we get 600. Then if we're going to take our 6s out 60 at a time, which is really 10 6s at a time, we get 120, we can do that twice. And then lastly, our units of 1. So this is something that I think probably feels a little uncomfortable. It feels a little confusing because we're using words about place value in places that maybe we weren't used to putting words about place value. And that's really why I want to introduce that and reinforce that here. Okay. My thoughts up to this point. You have partial quotients. You have the standard algorithm. You can convert it to a multiplication problem and solve from there. So you'd say 6 times something gives me 726. So what would it look like? Could we try to solve this problem using division? I have something times 6 gives me 726. So what times 6 gives me 6? 1. What times 6 gives me an answer that ends in 2? Well, it's not 1, 6. 2 of them could be 12. And then do we get another time where that happens? So 2 times 6 is 12, 18, 24, 36, 48, 60, 6 times 3, 4. I missed one. 30, 5, 6, 7. So that's 2 sixes. I skipped another one, didn't I? 12, 18, 24, 30, 36, 42, 48, 54. Oh my. I was just counting by 12s. I apparently couldn't quite handle 6 in my head. So we have an ending in 2 here, or we have 7 times 6 is 42. So this is either going to be a 6 or a 2. Will it be a 6 or a 2? Well, if this is 6, six times 6 is 36. Not 6. 7 or 2. 7 times 6 is 42. Have a 2, and then we'd have to carry a 4. If this was a 0, this would become a 4. If this is a 1, that's a 6. 6 plus 4 is 10. That doesn't work. If this is 2 or higher, we're going to have a thousands digit, and we know there's not one. So it can't be 7. It turns out, as we know, it's 2. 2 times 6 is 12. We have a 2, and then we carry a 1. Something times 6 plus 1 is 7. And in our case here, that something is 1. And so remember that problem off quiz 1, where we had the find the maximum, or no, it was find A, B, C, and D. You had to find the blanks. It gave you an addition problem that said, what real numbers A, B, C, and D make this true? That was another instance of this pre-algebraic thinking, but that's precisely how a child, or you, anyone really, could start to think about using multiplication as a way to solve a division problem. Is this less or more work? I don't really know. But in terms of concepts, multiplicative concepts are generally easier than division, and so there might be a way that this would help a child understand if they would otherwise. All right, let me go back just to slides for a second. So we had an addition table for our facts up to 20. We had our subtraction table with our facts up to, or no, we had our addition table with up to 10 plus 10. We had our subtraction table where we subtracted up to 20. We had our multiplication table, which was up to 10 by 10. And then we might have a division table. And actually, I'm just kidding, we don't have a division table. What we do is we use the fact, use the fact that multiplication and division are inverse. So if I have 7 times 6 is 42, right? This is a fact we know. You could get to it to your half tens plus 1, your 6 facts. 7 times 5 plus 1 more. 35 plus 7 is still 42. So if we have to find 42 divided by 7, we first rewrite that as 7 times something is 42. And as our work already showed, that something there, we'll erase that. That something that we care about is 6. So we don't have division facts, which maybe also makes me wonder, well, why do we use addition fact or subtraction facts? And the reason we specifically teach subtraction facts is because when we do our addition facts, we wouldn't get, say, 20 minus 6, right? That's not one that's going to appear in our addition table. And it turns out we care about subtraction up to about 20 in terms of rapid recall. But often we talk about addition, about getting things, and we talk about multiplication, duplicating things. So no division table. I don't have one to share with you. You could probably try to come up with one, but so let's think about what that would mean. Because we're working with whole numbers, we only would want the ones that gave us no remainder. Or if we wanted a remainder, now our tables wouldn't just have the answer. They'd have the number and the remainder. So it would be like, if 72 divided by 10 is 7 remainder 2, you would need to find the 10 column, the divide by 7 column, and we have remainder 2. But unlike all of our other ones, or rather more like our subtraction, we don't get to flip it, right? We can't just divide in any order. And you'll see, as was coming in this formal discussion, we don't have commutativity for division, just like we didn't have it for subtraction. But we do have all the properties we had for addition. We have, a unique product. We have a commutativity. We can move them around in any order and multiply and get the same answer. We have associativity. We can group things, multiply those first, and then move on without changing the answer. So our definition. Multiplication, right, relied on this definition of we have so many groups. Each group has a certain size, and that together gives us the total number of objects. Our definition for division is, for any whole numbers, a and b. B can't be 0. We can't divide by 0, and we'll talk about that in just a little bit. A divided b equals c. If and only if. So that's saying these two statements are equivalent. A divided by b equals c is equivalent to b times c equals to a. So rather, a divided by b equals c if and only if c, our quotient, is a unique whole number such that the divisor times the quotient gives us the dividend. Or the dividend divided by the divisor is equal to the quotient. And that quotient is that special number, there's only one of them, such that b times c is equal to a. And we have lots of notations for divides. A divided by b can also be written as a over b, which we call fractional notation, or kind of this standard division symbol, which is like this parenthesis with a long bar. I'd be interested to know where that came from, so maybe I'll do a little bit of homework and look up the history of the divide sign. So some special things, divided by, a division by 0 and 1, and I guess I only have 0 on this slide, so I'll add 1 by hand, but what we have is, let n be any non-zero whole number. then n divided by 0 is undefined. Now why? Why is n divided by 0 undefined? Well, let's think a divided by b equals c if and only if, or is equivalent to, b times c is equal to a. Let's make sure I kept those the same order. B times C equals A. Looks good to me. So A divided by B is equivalent to B times C. So n divided by 0 means, so this is n and this is 0. It says if and only if B 0 times C is our given n. If I have 0 groups, this is going back to multiplication. If I have 0 groups, doesn't matter how big the groups are, I'm going to get 0 on the other side because I have no groups. So our definition, I'm going to hop back. C is the unique whole number. There is no C. So it's that 0 times something gives us n. And so it's undefined. 0 divided by any number is 0. We can kind of do our rearranging if you would like. So we have n, 0, and A, B, and C. So we have A, B, and C. So we have n times 0 equals 0. If I have n groups, but they're all of size 0, it doesn't matter how many I have 0 at the end. So 0 divided by n is 0. And then 0 divided by 0 is undefined because 0 divided by 0, I'm running out of room, so if it's okay, I'm going to erase, no, I'll switch to a different color. 0 divided by 0, so that's our A and B. We have 0 times C is 0. C could be 1. 0 times 1 is 0. C could be 10. 0 times 10 is 0. So again, I'm going to go back to my definition. C is the unique, there's only one of them. 0 times C equals 0. This last instance of 0 divided by 0 is true for all numbers. True for all numbers. And so it's not unique. So we can't do 0 divided by 0. So what we end up having is n divided by 0 is undefined because C doesn't exist. There is no C that makes it true. 0 divided by n is 0 because you can fairly share nothing with any number of people. They all get nothing. But then 0 divided by 0 is undefined because C exists, but now we have too many. There are infinitely many. C could be any number, and it will still hold true. And so that's why we haven't really dealt with this issue of uniqueness when it came to addition, right? It's like we said it had to be, it could only give us one. We couldn't really see why that was the case. And so moving on to division, I think, helped us better see why it is that we need to do this uniqueness. It needs to exist, it's unique, and it needs to be a whole number. So those are 3 criteria that all need to be true. Okay, so that's really the formal things that we're going to talk about. In terms of mental math, Some strategies we have for division. Break up the dividend. So you're like, well, 7 eighths are 56, so we can just take all of those out. That's 700 of them. And then we need 8 more to get that 48. So we essentially just split 5648 into 5600 and 48. So I think when all of these words are already here on the screen, it's hard to see. So if I were doing this by hand, what would this look like, right? Like it's how, if I were solving this, how would I write this? So if I have 8 divided into 5, 6, 4, 8, I'd be like, oh, I see something. I see something with that 56. So I'm going to say, well, that's the same as 8 divided into 5600 plus 48. $700 times 8 is 5600. So we're good there. Plus 6 more of them. $700 plus 6, 706. So what you would do is you would break it apart first. You'd rewrite it in this pseudo-expanded form. I mean, it's expanded, it's just not expanded place value form. And you divide them by 6, or you divide it by 8, and you get your answer. And so this is actually one of those strategies that, so it says it's a mental math strategy. This is a totally reasonable division strategy you might use if you're dividing. Or we had that example earlier where, remember I was subtracting, and so subtraction, not multiplication, but I was like, well, I can't take 96 from 4 or 2 or whatever the number was. I was like, oh, but if I just look at those last digits, if I just look over here at 5600, I'm able to see 7 of those fit in. We have 2 more, using compatible numbers. So suppose we have 3 divided into 105. And you'll notice, just like this one I previously did, it involved me, the doer of mathematics, as recognizing the 7, 8, 56 fact family. And we'll talk a little bit about, we might talk about fact families later in the semester, we'll see. But how this one works, if we have 3 divided into 105, I'm essentially using something similar to partial quotients. I'm like, well, I know that 90 is a multiple of 3, and then I have 15 left over. Oh, that's also a multiple of 3. So we have 3 30s and 3 5s, get 35. And you could also use it where you're subtracting. And so this was addition. But maybe you have 8 divided into 232. And the reason we show this one is to show you that it does not have to be with addition. 8, 16, 24. So 240 is this kind of close number that I want. So I got there by doing this. 8, 16, 240. If you want, you can add zeros just so that we're going up by 80 each time. Doesn't matter to me. When I grade these on anything, I'm not going to grade your scratch work. So any way that you break it down, you record your work, I'm happy. I just need to be able to follow it and make sense of it. But I won't care if you write what numbers are over there. So 240. So this is the same as saying 8 divided into 240. And then we have to take some away. We take 8 of them away. 240 minus 8 is 232. And so we have 8 times 30 minus 1, which is 29. So 29 times 8 should give us our answer. 9 eighths are 56. No, they're not. 9 eighths are 72. 8 times 2 is 16, plus 7, 23. 232. Phew. I would have got, oh, you can't see that. I'll slide that up. 232. Yeah, it's real sloppy, but I was just checking my work. Because often, I just have to say, I'm more comfortable with multiplication. I like working with multiplication. And so, if my options are to divide it one way and then check it with the standard algorithm, or divide it and just multiply my answer to make sure it's right, I'm going to multiply. Because I could do 232, move this up, divided by 8. There are no 8s in 2. There are, however, 2 in 23. 2 8s are 16. We have 72. And then we have 9 of those. 72, subtract, and we get 0. So we get 29, which again matches our answer up there. But just in terms of effort, computational effort from me, this is less work to check the multiplication. But again, children should know both our options, and you should be able to choose the option that makes sense for you. I also think you should just be able to type it into a calculator and figure it out. All right, we're just one more, and this one's estimation, which I don't love how our book handles estimation. It just kind of like talks about it as this tack on at the end, and I'd rather talk about estimation across everything all at once. And so it's like, here's addition, here's subtraction, here's multiplication, here's division, and then here, this is what estimation looks like regardless of what we're estimating. But they're like, this is what addition is, estimation with addition. This is subtraction, this is estimation. And they just say, remember our compatible numbers from a couple slides ago where you're looking for numbers that are close? Well, if we just need an estimate, 3,700, pretty close to 3,600. There's 600 sixes in 3,600, and so we can just throw that 600 up there. And so that's really, those are our options for estimation, or you just kind of pick a number that's pretty close to it. So, where are we now in the course? At this point, we've talked about logic. It seems really dark if I have that off. We talked about logic. We talked about problem solving and logic at the very beginning. How do we know if something is true or false? And then what things are sort of equivalent. And that's going to set us up really for a solid foundation for proofwriting, which will be coming a little bit in this course, and then really heavily in 205. And this isn't an attempt to scare you. Because remember, proofs are just justifications. You're just writing down why you know what you're saying is true. But so we talked about logic and problem solving. And then we talked about sets. And we talked about sets because sets tends to be how we foundationally understand addition, the union of disjoint sets, subtraction, taking away from sets, multiplication, repeated addition, therefore dependent on sets, and then division, repeated subtraction, likewise, therefore dependent on sets. And so we have up through sets. And then we talk about number systems, particularly our base 10 system, thinking about place value versus face value. And then we've talked about addition, subtraction, multiplication, and division. But we had already learned those once upon a time in school, and so we took a slightly different look at them, and that's what we're calling this mathematics knowledge for teaching, or pedagogical content knowledge. It's the knowledge that you as future teachers need to know to be able to effectively teach mathematics. And so we step through each of our operations, what the concept of operations are, but we restricted ourselves to the domain of whole numbers. And so for the rest of this week, when we talk about prime and composite numbers, we're still going to be talking about whole numbers only. But then, starting next week, we're going to leave this restriction of whole numbers behind. First, so we can talk about negative numbers, and we can now subtract. Because remember, subtraction was defined a minus b if a is greater than b. It's that unique number such that b plus that number equals a, right? We specified our top number had to be larger than our bottom number because we wanted a whole number back. We wanted closure. We cared about closure. And so if we don't care about closure, I can take 7 away from 5, except now I'm going to get a negative 2. And so now I have to move to integers. Or then we're going to start to talk about, well, what if I don't need to be able to divide evenly? And what if I don't want to talk about remainders? We're going to leave the integers behind, and we're going to move on to the rationals, or our fractions, so that we can extend that operation. And then eventually, by the end of the course, we're going to be back to real numbers. And so, remember, that's this funny r that looks like this, the double-lined r. It looks like our z's, and those are our real numbers. Those are all of our integers, all of our fractions. But then fractions can be written as some number over another, but they're numbers like pi, the square root of 2, that you can't write in that way. And so we need to then loosen that restriction even more. And then what we end up with are all of the numbers we work with, the reals. And then if you take a higher level calculus or something where you're working with complex numbers, you start then being like, well, we can't take the square root of -1, but what if we could? And then you get I, right? And so what we're doing is we're building up from the foundations of sets, whole number operations, integer operations, rational operations, real operations. And that's the hierarchy, is whole operation, integer, rational, real.